Hello, this is our final project presentation. We choose BPN as our foundation to modify, and this BPN paper was published on CVPR 2020, and it's an oral paper. Here is the outline of our presentation. First, there is a challenge in real-world datasets, which is not always uniform distribution like most visual recognition datasets. A challenging visual recognition task is long-tail data distribution. That is, a few classes occupy most of the data, while most classes rarely have few samples, but it is very natural. And there are several related works to deal with this challenging problem: reweighting and resampling. Reweighting is changing the weight of the class according to the number of classes. Resampling is sampling more data from those small number of classes. These two strategies are frequently and successfully suggested to lessen a severe imbalance while dealing with long-tail difficulties. Although these methods are beneficial, there are some downsides. For example, reweighting can distort the original distribution by directly changing or even inverting the data presenting frequency. In resampling methods, if we oversample, there might be an overfitting problem on the tail data. And if we undersample, we have a high chance to underfit the whole data distribution. In the BPM paper, they reveal that the mechanism of these strategies is to promote classified learning significantly, but will unexpectedly damage the representative ability of deep learned features to some extent. They conduct a few experiments. First, that fix the representation learning method to be cross-entropy, and then change the classifier learning methods. As you can see here, the error rates decrease with resampling and the reweighting methods, and this is because it can improve the classifier. Second, they fix the classifier learning method to be cross-entropy and change representation learning methods. However, the error rates increase instead of decreasing, and this is because reweighting and resampling methods damage the ability of feature representation. Hence, they propose a brand new architecture. It has two branches, one of which is a conventional learning branch, and the other one is a rebalancing branch. After that, the predicted output of these bilateral branches are aggregated in the cumulative learning part by an added alpha parameter, which is changeable during training. First is the input of this architecture. The conventional learning branch is a universal sampler, which will sample data according to the number of classes. And the primary purpose of this branch is to learn the universal patterns of original distribution. The other branch, called rebalancing branch, which has a reverse data sampler, mainly deals with tail classes. And this branch improves the accuracy of tail classes. The author chose to use ResNet or backbone network. Both branches share the same weight except for the last residual block, and the last layer uses global averaging pooling to acquire feature vectors. They want to focus more on learning universal patterns, so they use cumulative learning to decrease alpha as the learning process persists. Here's the equation. T means the number of the current epoch, and the T max is the total number of the epochs. So the alpha will decrease as the training process persists, like this. And here is the output equation. W means the weights, F means features. So the output Z equals alpha times the weights of the conventional branch transpose times features of the conventional branch plus 1 minus alpha times weight of the rebalancing branch transpose times feature of the rebalancing branch. And then the output will go through a softmax layer like this. And here's the loss function equation. YC and YR are sample labels from two branches. Our motivation is that there are already two branches. One of the branches data input distribution is long tail, and the other is reversed. So that makes us wonder why they don't add another branch with a uniform distribution as its input. So we add a new branch with uniform data distribution as its input, and the model architecture is the same as the BBM branch, and the share weight with other two branches in BBN. Yeah, and about the alpha of cumulative learning, we just simply fix our new branch's weight controlling coefficient to 0.3, and then we modify 0.7 to its original branches. So the output equation becomes 0.7 times the original equation and the 0.3 times the new branch. And the loss function does exactly the same thing. We train our model on a long-tail CFR10 dataset with an imbalance factor of 100, including 60,000 images and 50,000 for training and 10,000 for validation. It's just the same as the BBM paper. And we train our network with three different ways controlling coefficient. And the results are shown in this table. Although we couldn't reproduce the results of BBM, the performance are not better than BBM trained by ourselves. According to the experiments, the idea of adding another branch fails. We think the reason is that the model will draw attention away from dealing with long-tail data sets, long-tail data classes. In original BBM, they just simply fix alpha in inference phase. So we adopt that and conduct an experiment on different profiles. The lowest error rate comes with alpha equals 0.5 when using the original BBM in the inference phase. We ended the author of BBM see eye to eye on the reason for it, which is that both branches are equally important. Here's the conclusion. What we have done is that we add a branch to the original BBN to see its performance, and we conduct several experiments, including different alpha settings and the different weight controlling coefficients of our new branch. And this is our reference and the workload separation. Thanks for your time listening to our final project presentation. We wish you a happy Chinese New Year.